All right, I think it's good time to start. Good morning, good afternoon, good evening. Welcome to the topology optimization webinar. Today is the 13th top webinar. It is organized by Professor Jun Yan and Professor Bin Liu from Dalian University of Technology. Thank you for organizing this, and the floor is yours.
So Jun, can we start it?
Yeah, please go ahead. Yeah.
Okay. Thank you for Professor Wu for your kind introduction. And so I think it's time to get started. Good morning, good afternoon, and good evening to everybody. And Professor Bin from Dalian University of Technology. And it is our great honor to be the chair for the 13th top webinar. And I'm very glad to meet our colleagues from all over the world here again and discuss some of the latest developments in topology optimization. And now there are, I think, about 60 people in the meeting room, and I think our field has attracted a lot of scholars' attention. Today we have altogether 5 very valuable topics from colleagues in this webinar. And so as the rule, each of the speakers will have 15 minutes to present, including a short Q&A. And there will be an additional question and discussion section after all the presentations. And during the webinar, if you want to ask a question, please notify us by shaking your hand or enter the question into the chat, and we will bring the question to the speakers. And I think I will first chair the first 2 presentation, and Bin will chair the latter part. And so thank you again for joining us. And next, let's welcome Mr. Bluhm from the Technical University of Denmark to deliver the first presentation. And the topic is internal contact modeling for finite string topology optimization. Let us welcome. So, Mr. Bluhm, can you share your screen?
Yes. So, yeah, thank you for the introduction. As said, my name is Lukas Bluhm, and my presentation is about internal contact modeling for finite string topology optimization. The primary motivation for this work is that contact-aware optimization is able to design structures while preventing undesired internal collisions, but furthermore, it also enables to utilize contact as a design feature in the optimization of structures with desired nonlinear mechanical behavior. Most obviously is a stiffening effect arising from contact between internal members, but contact can also restrict or force internal beams to buckle, and thus a softening behavior can be triggered as well. And finally, I think it can be very useful in the design of compliant mechanisms, because here it is relevant both as a design feature, but also for preventing undesired contact. There are some conceptual conflicts in the modeling approaches between optimization on one hand and classical contact models on the other hand. And I think this is why internal contact modeling has received only relatively little attention in the field of topology optimization. In brief, what I mean by conceptual conflicts is that classical contact models like augmented Lagrangian or penalty methods, they require to predefine contact interfaces, as I've illustrated on the figure as gamma 1 and 2 of the 2 contacting bodies omega 1 and 2. Further, one has to check for overlapping points, and then in case solve the involved contact kinematics. But the problem here is that the design is generally unknown and undiscrete during the design optimization and topology optimization. And this makes the application of classical contact models very impractical, as it requires to identify potential contact interfaces in the domain for every design iteration. But besides the mentioned classical approaches, there is the third medium contact approach, and it is characterized by being based purely on a continuum mechanical formulation. As you see on the figure, the gap between the solid bodies is modeled with the contact medium here shown as omega-3. The contact medium is generally very compliant, but when ultimately compressed, it becomes stiff and hence it is able to transfer contact forces. This means that there's no need to specify contact interfaces. And with some tricks, we can simply use the same material, we can simply use the void material as a contact medium. And this is a great advantage as the void material phase in density-based topology optimization is part of the model anyways. And this is what makes the third medium contact approach a good choice for topology optimization applications, because here we have some obvious similarities in the modeling approaches. The adoption of the third medium approach comes with some crucial aspects that needs to be considered. First of all, a suitable constitutive law needs to be defined for the contact medium, and in addition, we have the well-known issue of numerical instabilities arising from heavily deformed void elements in nonlinear topology optimization. These two aspects will be addressed in the following. When employing the already present void material as a contact medium, it is in principle possible to use the same material for the solid and the void phase. But this requires that an appropriate nonlinear material law is chosen. In this perspective, it is important that the material is chosen, that a material is chosen where stresses go to -infinity when the material is compressed towards zero volume, because this causes an infinitely stiff response independently on how compliant the material is initially. And as a result, it can transfer forces between solid regions and thus it facilitates contact. Actually, many hyperelastic materials have this feature, so a lot of choices can be made that can function as a contact medium straight away. But as already mentioned, large deformations in the void elements may result in numerical instabilities due to distorted elements. This I would like to illustrate on the C-shape example, where the structure is fixed on the left boundary and the internal area is filled with void material. The initial stiffness contrast between solid and void material is set to 10 to the power of -12. And I prescribe a negative vertical displacement on the upper right corner, gamma d. The reaction traction is then measured as Q. In theory, contact should be observed between the upper and the lower beam at a certain loading. But when I start the animation, it can be seen how void material is squeezed out of the opening on the right edge and the elements begin to bend. And way before contact would occur, I run into instabilities and the solver stops converging. From this example, it is evident that some kind of stabilization of void elements is required. The proposed solution in this work is a regularization method. And the idea here is to ensure void elements to stay regular by preventing undesired deformations such as warping and bending. To achieve this, the strain energy function psi is augmented by an energy term, phi, which is related to a higher order strain. I've shown the equation here, where h is the Hessian operator, so the second derivative of the displacement field describing these undesired deformations. Finally, we get the resulting virtual work expression, where the contribution of higher order strains is highlighted by the blue line. As one can see, I have also introduced some factors where I is an identifier function for void elements, kr is a constant factor to scale the regularization properly, and finally, the intensity is increased for compressed areas by the exponential factor, which is a function of the Jacobi determinant. With this, it is possible to model the void at ultimate compression, and this enables the void to function as a contact medium. Now we can see how the regularization actually behaves. And for that, we use the same C-shape example as before. The structure to the left, the regularization is not applied, so it's identical to the one that I've already shown. But now the interior void material is colored based on the magnitude of the higher order energy. In the middle, we have a simulation where the regularization is applied, and to the right, there's a reference solution. Here, the void is removed from the model, and the classical contact method is applied instead. When I start the animation, we see how the energy increases in the heavily deformed elements in the void when the regularization is not applied, while the regularization in the middle restricts the energy at almost zero, and the elements stay regular. And as a result, no stability issues are encountered in the middle one. Here I have stopped the animation at approximately 60% loading, where contact is encountered in the structure in the middle. This can be seen by the bottom beam being bended downward very slightly, while the reference solution is still in a pre-contact state. But when further loaded, as we see here, the reference solution encounters contact too. In general, we see that the third medium contact method matches the reference solution quite well, as one also can see from the load displacement plot, where the red curve represents the structure with regularized void, and the blue curve shows the reference solution. We see that the stiffness is increased slightly by the contact medium, and the contact point is less distinct. This indicates pre-contact interaction by transfer of forces and causes some minor inaccuracies. Studies have shown that this effect is even more notable when the design is non-discrete as it usually is in topology optimization. Obviously, inaccuracy is usually a downside. However, when applying the contact model to optimization, it might turn into a benefit because this interaction makes the problem differentiable such that the optimizer can take potential contact into account even for distant members. Now the contact model is applied to an optimization example. Here, the internal contact will be utilized for a structure with desired nonlinear load response. In the present example, we aim for a stiffening structure. I've set up a load displacement path optimization with two control points which are related to specific values of prescribed displacement. The objective function C is shown here and formulated as a summation of contributions from all control points. The aim is to minimize the squared difference between the actual traction Q and some desired traction values Q star. And this is done for every control point, and they are weighted individually by the weighting factors W. The design domain is illustrated on the figure. It has a fixed boundary gamma dH in the upper left corner, and on the bottom edge, there's a region gamma D where positive horizontal displacements are prescribed. The initial design consists of two separated low density regions, and this is chosen to guide the design towards a contact utilizing structure. The target traction values are illustrated on the load displacement figure. At 10% relative prescribed displacement, which is the first control point, the target is zero traction or zero stiffness, while the aim is some positive traction value at 15%. Now we can see how the design converges within 150 design iterations, and the optimized design is clearly a contact utilizing structure with two separated solid regions. It consists of a truss-like upper part, and the contact coupling is shaped like a hook to ensure that the two parts will not disengage. The load displacement plot shows the response of the very compliant initial design in blue and the performance of the final design in red. We clearly see a stiffening behavior from the optimized design, even though none of the two target points are satisfied. Instead, what we see is a compromise which is obtained between the two control points. And this compromise is controlled by the weighting factors that I've introduced earlier. And here we have weighted the first control point 10 times higher than the second one, and this makes the difference smaller for the first control point. Here we can see an animation of the deformed design, and it shows a very continuous transition from a compliant pre-contact response to a stiff structure when the two parts engage by contact. But even at the final step, we can still see an intermediate density gap due to the graded interface in the non-discrete design. This indicates that the structure would become even more stiff in a discrete setting. And this is what we look at here, where we see a post-evaluation made using a body-fitted mesh based on a 0.5 density threshold. Only the solid regions of the structure are modeled, and a classical contact method is applied. The obtained load response is shown as the orange curve, and now the contact point is very distinct, but shifted to higher displacements. As the threshold increases the geometrical size of the gap between the two parts by removing the intermediate density layer. And as expected, the post-contact stiffness is much higher compared to the non-discrete design. This post-evaluation proves the ability of the contact-aware optimization, but it also reveals some of the limitations that are related to the non-discrete design. Overall, I think that I have shown that the third medium approach is a well-suited contact model for topology optimization. And this is especially true because there's no need to define contact interfaces explicitly, and because the already available void material can function as a contact medium directly, or at least when regularized. Furthermore, I have a useful regularization is introduced to enhance the numerical stability of the void material and allows the required high compression of void elements. The post-evaluation again has shown some limitations, which are mainly related to the graded interface of the non-discrete design. But there are methods to eliminate the effect of the graded interface, such as mesh refinement procedure during the optimization with a simultaneously reduction of the interface width, or one can just take the obtained design and use it as an initial guess for a shape optimization procedure. And that is what I had for the presentation today, and I want to thank you for your attention.
Thank you, Mr. Bluhm. This is a very interesting presentation. So now it's time to discussion. One or two questions.
The problems with the voice.
Okay. Yeah, some problem with.
Okay. Yeah.
Maybe I can start with a question. Lukas, thank you for a nice presentation. I'm wondering whether this third medium approach is able to handle friction. I think that will be an interesting future work.
Yeah, so for now, there's no friction in the contact. But I think that one could add some anisotropic property to the contact medium, so that is when it gets compressed, then there will be some stiffness in the normal direction of the contact, on the perpendicular direction of contact, and then it could mimic some kind of friction between the contact surfaces. I think it's possible to do that. Yes.
Well, makes sense. Yeah. Thanks for that answer.
Okay. Any more questions?
I also have a question.
Okay. Yes.
So, Lukas, thank you very much for an interesting presentation. I have a question. So, this model, I mean, how sensitive is it to the amount of elements that get squished? Meaning, let's say you have 10,000 elements between the two contact surfaces. Would that give a significantly different response than if you only had a few, like in the examples you showed?
I wouldn't expect it to have a significant influence. I haven't checked with 10,000, but I think in the example here there are quite a few. I mean, it's probably 10, and I've seen examples with even more. But I mean, for sure, not more than 50 elements in the contact region.
Okay, so maybe my question is more like this actually. So do you have a measure for the gap between nodes that are being forced together or elements that are being squished? Can you quantify it such that you could actually predict it?
Predict what?
Sorry. The gap. between the contact surfaces. I guess you will never have perfectly coinciding nodes, right? They will always be apart by some small. Yeah. Can you compute that based on your parameters such that you could tune it?
Not as far as I have tried, but so you're referring to if you have too many elements in the gap, then the contact will be at even a higher distance than shown on this example.
Exactly, and just speculating that if this was something that the optimizer at some point could utilize, if you go very large scale, I would just predict it could. So I'm just curious if you could predict that little number or the small number.
Yeah, probably. But again, I think if you look at this one here, then the gap is dominated by the intermediate density layer and not directly by the real void material, if one may call it like this.
Good point, Lucas. Thank you very much.
Okay, thank you all. And due to the time limited, and we must move to the second speaker. Thank you. Oh, and Professor Junji, would you like to share your screen? And the next speaker is Professor Kato, Junji Kato from Nagoya University. And the topic of his presentation is robust topology optimization based on finite string, considering uncertain loading conditions. So, please, Professor Kato.
Okay, can you hear me?
Yeah, no problem.
Okay. So it is 11 o'clock, midnight. I'm very sleepy, but I'm fine. Okay, thank you very much. So thank you, Jen, for your good introduction. My name is Junji Kato from Nagoya University, Japan. And it's my honor to have a chance to give a presentation here and to introduce our work here. And this work was done by my former student, Mr. Nishino, but unfortunately, he graduated from university. He's working now. So I want to introduce his ongoing work. Still, we are doing this work. So I'm going to introduce part of current work, and in addition to the content written in this paper. Okay. So typical uncertainty in structural problems may be initial perfection, material properties, load side, location, angle. So in this research, we focus on certain uncertain loading angle. Okay, we focus on only angle. So this is the example of maximization of stiffness. Okay. For ideal vertical load. However, what happens if the load angle is changed uncertainly? So this situation often occurs in reality. So in this case, mean compliance may jump. Okay, may jump depending on the uncertain loading angle. Okay. So this is not good situation. However, once we use our two legs structure, the compliance should be, the change of compliance is not so large. Okay, this is a basic concept of this robust design in our study. So there are several very nice papers here. Okay, I just pasted just 3, but there are other nice papers, of course. But most of them are based on the linear elasticity theory. So what we want to do is simply to extend to the geometrical nonlinear problem for uncertain loading angle. That's it. Very simple purpose. So this is our objective function CR, here CR. And then C is end-compliance. And E is expected value, and V is variance. Therefore, root of V is standard deviation. The alpha is weighting parameter from 0 to 1 in our case, and C is end-compliance. F is the external force vector, and the U is displacement vector. And load angle theta is defined as the random variable following to the normal distribution in our case. So minimizing, so once we minimize the standard deviation, this part, maybe change should be reduced. Once we minimize the expected value, this end-compliance value should be reduced. Okay, therefore, we want to minimize both terms together. So I simply applied simple approach here, so nothing special. We applied the simple approach. And the equilibrium equation here, and the volume constraint is also here. Okay, nothing special. So what we propose is simply the approximation of end-compliance. Here, C, end-compliance C is F multiply U. Okay, and we apply the random variable theta. The theta bar is mean, and the delta theta is the deviation. Now we take our second order Taylor's expansion here. And then C is approximated like this. So this is the first term, zero order derivative, and the first order derivative C1, and the second order one, C2. Okay. And also we approximate moments together. So EV is approximated like this. So fortunately, these terms can be obtained easily because we follow the normal distribution. Therefore, this term can be immediately obtained. So what we have to calculate is simply C0, C1, and C2 only. In particular, our C1 and C2 is a little bit difficult to obtain. Therefore, I want to introduce how to obtain these two coefficients. So zero order derivative C0 is nothing special, okay, and the compliance itself. So C1, so first we have to take a derivative with respect to theta. Of course, we will have implicit term. Therefore, we applied the adjoint vector for this problem and take a derivative. And then in this situation, we use this relationship. So residual force R with respect to theta is 0. We apply this one. Therefore, using the adjoint variable lambda, the first derivative can be obtained like this. So lambda can be obtained by solving this adjoint equation. And the second order derivative is like this. So we start from the first derivative. Okay, this is a completely the same equation as before. Okay. Now we add two terms. And mu and nu is again the adjoint variables. And then take a derivative with respect to theta. And we applied the second derivative of R with respect to theta. This is also applicable relationship. Then, after solving this mu and nu with these equations, we simply obtain our second derivative. For the sensitivity analysis, I mean, derivative with respect to design variable also can be obtained like this. Okay, so fortunately, this blue, orange, violet, and the green bracket has already been introduced here. Therefore, they can be used in sensitivity analysis. Okay. So I want to introduce examples. So first example is very simple. This is both cramped structure. The one force is on the top at the center, and this force seems to be vertically subjected, but this vertical load has some angles. Okay. This one is deterministic design, like this. Oops. And this one is robust design. In this one, alpha equals 0. This means that the only expected value is considered. This term is gone. For robust 2 design is alpha equals 1. So E and root of V both are considered. Okay. In this case, very thin members increased. Okay. And this is a graph. So blue one is deterministic one, and green is robust design 1, and the red one is robust design 2. As you can see, robust design 2 has small jump compared to other 2 cases. And next example is simply the comparison of the small string and the finite string. Okay, it's a simple structure, and I applied 2 kinds of force, so compression force and the tension force, and also I tested with different standard deviation of the loading angle and also weighting factor. So this is the result. So this is the for a small string case. So this is deterministic design. So this is standard deviation. Okay. So for the nonlinear case, compression case, so 2 legs appeared, and then it seems to be like not arch, but like an arch. Okay. For tension case, this is the 2 legs seems to be a little bit different from compared to the compression case. Maybe this figure is understandable. Okay, so this is a compression tension case. The once uncertain loading angle happens in compression. So 2 legs becomes like this. For tension case, yeah, knock seems to be good. Okay, so I think you can understand the situation. And I just compared the structure designed by and the linear elastic case and non-linear case. I took 95 degree of load, and then I continuously calculated with the nonlinear structure analysis, and then nonlinear design showed good performance compared to the design, the structure designed by linear elastic case. This is also another situation. Okay, I just take 105 degree of load. This is compression, and this is also tension. So we always have a better performance in nonlinear design. Okay, this is a final result. I just extended to the 3D case. Okay, so again, this compression and tension and the load is also uncertain like this. Okay, this is a case of the compression. So deterministic design is almost a bar structure, column structure. And then in robust design, we obtain this kind of structure. For tension case, you see, you can just look at difference. There's not a big difference actually, but you can see shape is a bit different, okay, between our tension and the compression. Okay. Okay, I would like to conclude this talk. So we developed the topology optimization method based on the geometrical nonlinearity considering uncertain loading angle, and also approximation of objective function by tailored series make it possible to obtain optimization results with relatively small computation. And each coefficient of tailored approximation can be analytically obtained. Completely analytical expressions are proposed by a joint approach. And also we have already tested for the different uncertain problem, uncertain load size. Okay, and we obtained the result, but I want to skip this story. Finally, we are now implement the problem, typical problem of the finite string case. I mean, mesh is always distorted, and then calculation stop. So we are now improving this problem. That's all my talk. Thank you very much.
Okay, thanks a lot, Professor Kato, and it's a very interesting presentation. And some short questions. Any questions or comments? Okay.
How about the computational cost for these second derivatives? I guess it's that sounds a little expensive.
Yeah, expensive, but how can we express how expensive it is? But yeah, of course, expensive, but it is not so expensive because analytical expression and yeah, maybe just twice compared to the conventional nonlinear geometrical nonlinear topology optimization, just twice or like that. But in 3D case, in 3D case, it takes more. But nowadays, our computer is getting better and better. we don't take care so much about the computational cost. Actually.
Yeah, I'm not sure about these calculations, but otherwise, when you compute ordinary Hessians, then it scales. It scales with the number of design variables. Can you get around that here? So. A big adjoint calculations doesn't scale with the number of, then it's independent of the number of design variables. But but for the second derivative, do you get this higher complexity? So then, so is it only how many adjoint do you have? Adjoint problems to solve?
Yeah, in this case, for example, 3D case, element number is like this. It takes 3 days, something like that.
Yeah. So I understand. Okay. So it is expensive. Yeah.
Yeah. Of course, it depends on the computer that you have.
Okay.
Sorry, it's not the exact answer. Sorry.
Okay, thanks, Kato. And due to the time, and we must move on. And Bing, would you like to chair the next 3 presentation?
Yeah, thank you. So we are a little bit behind the schedules. So let's welcome the third speakers from USA University, Illinois, Professor Shelly Zhang. She is going to talk about multi-material topology optimization of considering large deformation. Let's welcome. Please go ahead, Shelly. Please.
All right, can you hear me?
Yeah, yes, no problem.
Right.
Go ahead.
Okay, thank you, Bing, for the very nice introduction. And I'm Shelly Zhang, and I'm assistant professor from University of Illinois at Urbana Champaign. So today it's my pleasure to show you a recent work that we have done to in this top webinar. And so what we are going to present today is we establish an adaptive multi-material topology optimization approach that can optimize multiple types of hyperelastic materials and large deformations. And this work has been published in CMAME, and my co-authors are Dr. HengChi from Siemens Corporation Technology, as well as Dr. Glaucio H.Paulino from Georgia Institute of Technology. All right, let me first give you a quick motivation or introduction of this work. So why do we care about, why we want to work on the multi-material topology optimization? So in fact, many engineering structures typically contains different types of material phases. And this is true at various scales. From as large as the airplane, for example, on the top left, to as small as multiple types of metamaterial systems. For example, on the top right, we have this metamaterial that consists of two phases to realize a negative thermal expansion. And we can also, by using the multiple nonlinear materials, soft materials, we can also program the different buckling pattern, which is shown on the bottom left. And sometimes we don't even need to consider multiple material phases, but consider the various local porosity. Even using the same material, we can manufacture a structure that can move without any mechanical joints. And here is an example I'm showing on the bottom right, a work from the Disney lab. All right, so we are particularly interested in developing a systematic approach to design the composite structures considering multiple nonlinear elastic materials, because it has tremendous potentials to realize different functionalities in different applications. And this slide summarizes the formulation we propose for the multi-material topology optimization, consider finite elasticity. And here you can see that for the objective function, J, on the very top, it is a general function and can be chosen according to different design target, for example, stiffness or target deformation. And here we introduce a set of M candidate materials. Each material is associated with a set of design variables. And for material I, the corresponding set of design variable is rho I. And here we also introduce a set of multiple volume constraints with a general setting. So the total number is represented by NC. So in the NC can vary from all the way from NC equals to 1, which represents a global volume constraint for all the materials, all the way to NC equals to M, which means we put individual volume constraint for each material. And then the equilibrium is ensured by minimizing the total potential energy. And here, as you can see, the potential energy here consists of the contribution from all of the candidate materials. All right, and on the bottom, I'm showing a quick illustration of the multi-material setup. So for example, if we have a design domain, and then if we can consider an arbitrary number of candidate materials, in this case, we have 4 materials. So that's why M equals to 4. And we can also group different materials into the different constraint. For example, the first 2 goes to the first constraint. The last 2 goes to the second constraint. All right, so in order to effectively solve this problem, we identify 3 challenges that we need to address. So the first one is we need to, because we want to consider multiple materials with nonlinear behaviors. So we have to interpolate multiple nonlinear materials, because now the material is not characterized by elastic modulus. The material parameter is characterized by the nonlinear function of deformation. The second challenge we have is we need to model the large deformation behaviors, which means we need to address the excessive distortion of low density elements. And the last challenge is we need to be able to optimize these multiple materials and constraints, which means we need to have an update scheme as well as a very efficient modeling technique. Let's go through each one. So let's start by looking at the material interpolation scheme. So as I just mentioned, the material right now, because it's a nonlinear elastic, so it can be characterized by different type of store energy functions. So in this case, this W1, W2, 3, and 4 can be of various forms. So the way that we interpolate this store energy function is to use this W row here. It collects the weighted sum of all the store energy function from each of the material phase. And here the Wi here, the weight here is determined by this discrete material optimization technique. And the idea is that we not only want to penalize the gray regions, we also want to penalize any mixture of 2 materials or more materials. All right, so we address the material interpolation scheme. Let's look at how we address the excessive distortion of low density. So in this work, we use this energy interpolation scheme proposed by the group from Denmark, from DTU. And the idea is that for the regions with the low density elements, we will use the linear elastic models. And for the remaining regions, we will use the original nonlinear material, right? And then in this case, we apply this energy interpolation scheme to multiple material system. So in this case, we need to obtain this, the parameter gamma is to determine which region is nonlinear, which region we treat it as linear. So that is calculated through this summation of the filtered density variable to the power of p. And here on the bottom, I'm showing an illustration. So on the bottom left, suppose we are at an iteration with 4 candidate materials, and then we first perform this calculation, and then based on that calculation in the middle, we obtain the gamma, which tells us where we have the nonlinear material, where we have the void regions. Okay, so the next part is the optimization update. So here we didn't use the commonly used MMA. Here we derived a tailored optimization update scheme for the proposed multi-material formulation, and it's called a Zipper design update scheme. And the basic idea is that we realized the fact that the Lagrange multiplier, for each constraint is fully decoupled. And then the update for the design variables for each constraint can therefore be updated completely independently. So what is the nice thing about this update scheme is the update for the design variables for each constraint can be done in parallel. And that's what we did. All right, the last part is the simulation. How do we handle the, how do we model this nonlinear behavior and so on. So in this work, we use the virtual element method. I'm not going to the details of the virtual element method in this presentation. The details is shown on the bottom left citation. The key idea here is the VEM, the virtual element method, is a generalization for the finite element approach, which the VEM can handle the generalized element shapes. So we use this key point, this key advantage to enable this mesh adaptivity, because we don't have to do any special treatment for the hanging nodes if we do any refinement or coarsening. Here on the top, I'm showing the process of the adaptive refining. And you can see that wherever we have the material, we have this refinement. On the bottom, I'm showing the typical adaptive coarsening step. And then one thing I want to point out is we only have the refinement. So by using the combination of refinement and coarsening, we only have the refinement to where it's needed. For example, the boundary of the topology, as well as the interface between two materials, as you can see on the bottom right. Okay, let's take a look at some design applications. So here, the first application, we worked on the optimization to maximize the potential energy at equilibrium state. So this is similar to in the linear case, it is the same as the maximizing the stiffness. All right, so we use a cantilever beam, and we consider a total number of 8 ogden-based materials. And here we use 3 cases. The first case, we have 2 materials. The second case, we have 4 materials. And the last one, we have 8 materials. So here, let me first show you the mesh adaptivity history. You can see that from the optimization history, we can see the evolution of the number of nodes. And then you can see on the right, I'm putting 3 snapshots of the deformed meshes under the mesh adaptivity. And you can see that at the end, we are able to obtain you can see that the refinement only happens at the boundary of the topology as well as the interface of the materials. All right, and we work on this problem using 2 magnitude of the load levels. First is F equals to 20. That's the first row, top row. Second is the larger load magnitude to have this larger deformation. And you can see that I just want to point out for the 3 cases that we consider, 2 material, 4 material, and 8 materials, you can see the difference of the material distribution comparing the larger deformation and the relatively smaller deformation. So we can see that the proposed framework with the energy interpolation scheme works well to handle the large deformation. All right, the last example I'm going to show is the compliant mechanism. In this case, we are considering 4 ogden-based materials. And then, so with different type of the green one, the yellow one is the tension dominated, and the red one is compression dominated. And as you can see from the optimized design, 2 materials are chosen. And you can see the yellow material is chosen because it's tension dominated and is placed at where the member is under tension, and so does the red material is chosen for the compression. All right, so today we show that this propose this multi-material topology optimization framework. It is a design tool that not only optimizes the shape, but also the selected proper type and the amount of materials, and handles an arbitrary number of nonlinear materials with the distinct behaviors, and capture nonlinearity in the material and the geometry, and perform the efficient update. And before we finish, I just wanted to show you some recent development related to the work I'm presenting today, which uses the multiple nonlinear materials and under large deformations. So the one on the left is this fiber. We worked on a fiber reinforcement, hyperelastic structures, and we optimized both the matrix and the fiber, underlying fiber orientations. And then on the right, we show that we are optimizing the composite structures with programmable elastic response. So we have a target here shown on the right, and then we have a design. We are trying to minimize the errors between the target and the design. And here we show a simple example by using two highly nonlinear materials, blue and the red. We are able to optimize the distribution of the two materials, two highly nonlinear materials, in order to precisely achieve linear behavior. So the references are provided below for both of them. Thank you.
Okay, thank you, Shelly. Maybe one question?
All right, please.
So, Shelly, and it's a very interesting presentation. My question is it possible for the adaptive meshing technology can weaken the stress concentration between the material interface?
I think it will weaken. Usually for the material interfaces, we will have the refinement. So if we keep refining it, we will run into the situation. Maybe we will have higher concentration of the stress between the two materials. Yeah. So we'll not have will not alleviate, but I think it will probably capture more accurately.
Thank you.
Yes, we have some questions from the chat room, but I think we can discuss in the final general session. So Shelly, thank you again. So let's welcome the fourth speaker from TU Delft, Emil. He's going to talk about the topology optimization for 3D printings. Let's welcome.
Okay, so good afternoon. Yeah, so thank you for the invitation. I was asked to present some work that is actually done already almost 2 years ago, but was recently published. This was on the accessibility of supports, which I did in the group of Fred van Keulen. And this is all about topology optimization and additive manufacturing, and it's actually closely related to a talk of last month. And so a last body of my thesis was actually about overhang filters and overhang constraints. But while we were working with a student on these manifolds, so this is work from Jeroen Verboom, we actually noticed like, oh, it's actually not that bad to have supports if they are easily removable. But inside channels, that's really a nightmare to get out. So we thought, okay, can we make the overhang a little bit less strict by only applying it in regions where you really cannot remove these supports? And we came up with this quite simple method to do it. Actually, we came up with a rule that says, okay, we only accept supports if it can be connected to the base plate. And as such, you allow situations that you can see here on the left. So this is fine. We can remove it after the print. When the supports are inside an enclosed void, then that's not allowed, and that is also similar to the talk of Shutian Li last month. But we also don't like supports, even though they're not in an enclosed void, but if they are in a long channel. And so by enforcing that the supports have to be connected to the base plate, we also don't allow these kind of supports. And in order to do this, we came up with a filter scheme that actually is a clever rearrangement of the overhang filter and a couple of Boolean operations. And so in order to implement this, you need an overhang filter. And since a large body of my thesis was actually about overhang filters, we are using in this presentation the front propagation-based overhang filter. Although that's actually not in this presentation, it doesn't really matter as long as you have a filter that can remove material from a geometry that is basically removing the material that is not printable. You're absolutely able to implement this method. although it is really nice to have an overhang filter where you can handle variable overhang angles and weird unstructured meshes, but that's besides the point of this presentation. So let me show you how we implement this. As you can see, the structure on the top, we have two overhanging regions in red. The one in the middle is in an enclosed void, so we don't want that. But the one on the right, that's actually fine because it then can be supported by supports that are connected to the base plate. And so the filter scheme goes as follows. We start by adding some space from on both sides for supports to creep past the structure. Then we invert the structure. And then what you get is all the locations where you might be able to build supports. And then we apply an overhang filter. And this is actually already where it happens. So now we remove all the supports that cannot be printed and actually also that are not connected to the base plate. In the next step, we combine this with the original structure, and then we get the original structure and all the printable supports. Then we again remove the overhang, and now every material that is removed is really not being able to be supported by supports we can remove. And finally, we want to remove these supports by doing an intersection with the original geometry. And then you can see in the final result, we have what we want. So in the void, we get an active overhang filter. But on the right side, we do not have the overhang filter active because actually we can remove those supports. So it's quite a simple idea. If you have an overhang filter, it's also not that difficult to implement. And here you can see a mathematical overview of the of the filter. So this invert method, it's straightforward. It's just 1 minus your design. Then the overhang filter. Combine is a little bit more tricky because you want to make sure that that your densities don't go above 1, but basically that's this operation. It's also local. Again, the overhang filter, and then the intersect is easy. It's just multiplication of the two density fields. And one part of the paper is about this subject, but also a part is about how to implement such a filter structure in a nice way, such that you're able to basically play a bit with this and do it in an object-oriented way. And ever since I made that paper, I wanted to make some sort of interactive way of doing this. And this talk was actually the perfect excuse to start developing that. So I'll show the rest of the presentation in a live demo. And so what you see here is basically a canvas in which you can make your topology optimization. And the philosophy here is that really everything is a filter. So even the finite element, I see it as a filter where you come from densities to displacements or to compliance. And I think the best way to show it is just to start implementing a compliance minimization. So we start with the start. On the left, you see the filters we have in place. And so, of course, we start with the density filter. You can just connect it. And then the next block will be an expression filter. And here you can just type any expression. So let's add a lower bound and then sim penalization. So we do it to the power 3. And the derivatives will go automatically, basically symbolically, so you don't need to worry about it. Then linear elasticity. So this is the finite element, where the finite element solution happens. So we put the densities in and outcome displacements or the compliance value. And this goes directly into the objective, which is basically sort of the end stop. And then we also need the volume constraint. And inside there, we put also the filter densities, which we integrate over the domain. And then we put that into a constraint, which is also an end stop. And we put it at 0.5, and then we normalize with the area. And then finally, we have this scope block, which is a bit inspired by Simulink, I must say. And this you can tap into any density field and see what happens. And so if I now run, you can see that actually the optimization is happening live, and it's sort of interactive as well. So for example, if you look at the loading, that's now at the bottom row. And so if I change that to the 13th row, that's somewhere in the middle. Oh, wait. Then you can see the load is shifting. Yeah, so this is working quite nicely. But of course, compliance is not what I was coming to present. So let me make a little bit of room. And oh wait, I need this one to there. And let me introduce the overhang filter. So if I put the overhang filter after the densities and then put the overhang filter into the sim block and into the volume constraint, then you can see what happens if we apply the overhang filter. So this is the difference. You can clearly see the 45°. And if we restart the optimization, you now get a field where the overhang filter has been active. Actually, one of the reasons I also like to show this is I've been out of academia in industry for 2 years now using the commercial packages. And I would really like to have a package that is presented like this, where you can just arrange the filter blocks and also add custom filter blocks. So please implement it like this, because that just is so much more useful and customizable. Yeah, and now you can see the end result is sort of a printable structure. This arm, I think if you wait a bit longer, will get either more solid or will disappear. Let's not wait for that. Okay, so I'll open the link again, and if you want, you can try it out yourself. By the way, it's just on the internet. And I clicked together the accessibility filter a bit earlier because that's a lot of work to click together. And here you can see that it really pays off to implement like this, because you can easily experiment and swap things around, see what the effect is. And I'll show you the filter once more, the accessibility filter on a result from a compliance minimization. So let me run it for one step. So you can see we start with a density filter. And first step was to create this room on the sides. So we do that by fixing the densities to 0 on the edges, and also for the finite element solve, we move the boundary conditions inward to not have them on void elements. Then we invert, that's just this expression block of 1 minus the densities. We get this space for the supports. We put the overhang filter over it, so then we get the printable supports. Finally, we combine it, so this field with this field to get this last one. And then we again add the overhang filter to arrive at this block. And then we want to remove all the supports, so we multiply both fields. So that's, let's see, that's this field with this field to get to the final field. So let's run it from scratch and see what happens. And so here you can see the scopes updating left to right. And basically what's happening on the background is it's doing a sweep. So it's basically a directed acyclic graph, and it's going through that. And then when the forward is done, it starts at the constraint and the objective blocks and goes in the opposite direction. Applying the chain rule is what it's doing. And yeah, and you can see here in the end that this final block, so this is the accessibility filter design. You can see that the overhang filter is indeed active inside the void regions. So there it's enforcing this 45° rule, but not on the outside. So this member is clearly violating the overhang constraint, and this one also. While if you would do a pure overhang constraint, yeah, you would have to use more material to get that to comply with your filter. So it looks like this member is also going to disappear. Yeah. So I'll show quickly what happens if you would just use the overhang filter on this design, because then it becomes clear what is actually violating it. So then we put it like this. And here you can see, yeah, so here, if you would have the overhang filter active everywhere, these regions would be cut off. And so yeah, this is basically what I wanted to show you. In the paper, we also show that this method works nicely in 3D as well. Not yet on the website, that's a bit too much, but perhaps in the future. And I think it's a nice, if you have an overhang filter in place, this is just a small effort to put in, and it makes it much more usable actually. And this is what I wanted to show you. Perhaps I put it on a larger case in the background, and I can take some questions if there are any.
Emil, oh, sorry, June, maybe you first.
Yeah, please go ahead, Niels.
Okay, yeah, Emil, thank you for a very interesting presentation. So I I have a few, maybe let's start with one question and see where that takes us. So I really like this modular stuff that you're doing. Of course, from a research perspective, I wish we had more time to do these kind of things, but that's why we need people like you in the industry sitting with the need and the time maybe to actually assist in getting it out there. So let that be a hopeful request that you would continue this kind of work in the future. No, but my question is, so this is based, if I'm not mistaken, on the convolution type filter, right? So the operation that you do requires some neighborhood search.
You mean the overhang filter?
Yes, all your filtering operations, right? From the density into the overhang, or am I mistaking something here?
Well, this is all these filters are so it differs a bit. So the density filter is just your just a regular like top hat filtering function. So indeed, there you have a convolution.
Yes.
The expression block is local, so that's just a density operation.
Mm-hmm.
And then the overhang filter indeed is again a global type of filter where you sweep to your structure bottom to top.
So my question is, for the overhang filter, could you think of an equivalent PDE problem you could replace it with, so you could go large scale and avoid the search? I mean, convolution type filters for very large scale problems. You cannot do that.
Actually, so the way I implemented it, my thesis was basically on this, and what I did was I formulated this as a front propagation problem, and then you get the PDE, so it's a continuous equation where you can do this, and so yeah, but and that yeah, so yes would be my answer.
Okay, good. Thank you very much.
Jun, I suggest you can ask afterwards. So let's continue. Yeah. So the final talk will be from Junyi Duan from Northwestern Polytechnic University in China. He's going to talk about reliability-based multi-skills design optimization of composite structures. So Junyi, go ahead.
Okay, Zunyi, I want to turn on the mute.
Okay.
You must. Okay, that's all. Okay, please.
Sorry to thanks Chairman and the organizer and all the audience for your attendance. I'm Junyi Duan from Northwestern Polytechnic University, China. The co-author of this research is Dr. Yongxu Jiang and Professor Yi Zhenli from the CAST Republic of Korea and Professor Jun Yan from the DUT China. The title of this topic is reliability-based multi-scale design optimization of a composite frame, considering the structural components and the manufacturing constant. The presentation will be introduced by four parts. First of all, I will briefly introduce the motivation and the introduction. Composite framed with their excellent material properties such as high strength, stiffness, and anti-temperature correlation, particular and good damping has been popularly used in engineering applications. Besides their excellent material property, composite framed structure has a feature of large scale, flexible, and easy expansion. So it's an ideal structure for satellite mean load bearing frame at the right corner picture show. Meanwhile, in nature and the architecture structure, we also find that this structure has the special microstructure, such as the femoral head and Eiffel Tower, especially the right corner pictures, the femur with the fiber winding microstructure. So with nature inspired, in this research, we want to combine one piece of structure design and material design together. In structure design, we can carry out size, shape, topology optimization, and for composite material, In material design, we can optimize the fiber content, fiber laying angle, and layer thickness to realize the concurrent material design optimization of laminate composite. However, in real engineering application, we needed to consider the design for real with considering uncertainty. Because uncertainty is inevitable and pervasive in this aspect. So without considering this uncertainty, the optimized deterministic result is poor performance and high reliability of failure. So for composite framed, we can in structure scale, we can carry out the size and the topology optimization with considering the radius of the composite tube as macro scale design variable. And in material scale, for discrete fiber laying angle with adopted MO interpolation scheme, we can carry out the fiber laying angle selection. And considering the uncertainty of loading the magnitude and the direction and the material property to carry out the reliability-based multi-scale design optimization of a composite frame. So for the second part, I will briefly review the reliability optimization and the proposed method and the mathematical formulation. The general RBDO model can be formulated as this formulation with probability constraint. And the purpose of RBDO is to find the optimized gen that the probability of failure in each constraint has to be less than the target probability of failure. And in methodology, there are two major ways to evaluate the probability constraint. One is reliability index approach, and other is performance measure approach. So the corresponding MPP most probably point updating the scheme that can be shown on the left and right test rectangle. And in present research, the PMA performance measure approach is adopted. According to solution strategies, the reliability optimization algorithm is divided into three types: capital loop, and the single loop. The following show some famous and representative methods, such as safety factor post, sequence optimization reliability assessment proposed by Professor Du and Chen, and the single loop method such as SL, SV, and SLA method. In this research, the SL, SV method is adopted. So the main innovation of SLSV approach is approximate the MPP point at each design point by the following formulation. In this formulation, the SLSV approach use the gradient information of a performance function to approximate the most probability point. So compared with double loop, the efficiency is definitely improved. But for high nonlinear performance function, it will suffer the large error problem. So when we use the SLSV method, we should consider this issue. So in this research, we propose a modified single loop, the single vector approach based on MMC modified classical method. The MMC is originally developed for double loop RDDO optimization. This formulation show how MCC method has the new direction of MPP. So we combine the advantage of SRV on efficiency and MCC on accuracy together at the new MPP updating the formulation and the proposed SLSV MCC method corresponding formulation can show as list equation. Then in this research, the other issue is how to consider manufacturing constraint, because in this book about composite material design, they mentioned some of the manufacturing constraint should be considered in design. So with adopted DMO method, we simulate this manufacturing constraint, such as symmetric, balance, and the 10% constraint as the linear equivalent and inequivalent constraint. So as with considering the all the former mentioned model and manufacturing constraint, we can build the mathematical formulation for multi-scale reliability optimization. The objective function is minimum structure cost, with considering the structure compliance constraint to like the structure compliance, the reliability of failure of structure compliance, small target failure, and the corresponding manufacturing constraint can be formulated as list. Okay, let's go to the third part, numerical example. In the numerical example, we in the numerical example, we consider the uncertainty of material property and the loading the condition. The loading condition contains the magnitude and the direction, and the form and the SLSV method are adopted to compare with proposed method. The Monte Carlo simulation method with the 100,000 simple to validate the accuracy of the proposed method. And there are contained 7 kinds of content. One is reliability compliance content, and the other are manufacturing constraints. So the first example is an EJ4 beam composite frame. That can easy to image the result of final optimization. The left picture is deterministic multi-scale design optimization model, and the right picture is a reliability model with consider the force, the magnitude, and the direction uncertainty. And the target failure is set at 5%. Full quantitative materials are considered as the fiber winding angle, and in modified choice control, the stabilization factor is set as 0.7. So the picture shows the optimized topological configuration for different methods. As you can see, there are 2 types for deterministic optimization and SLRV. The topology configuration converts to 2 beams, and for form and the proposed method converts to 2 beams the structure. So with this table show the value of the radius and the MPP, the most polling point, the direction result. So as you can see, the formed and the proposed method at a little larger the loading the direction. So further to full beam the structure, and for deterministic multi-skilled optimization and SL conventional SLSV, the loading direction is small, so converts to two beam example results logic integration. And this table presents the material comparison on the efficiency and accuracy. We can conclude that the proposed method show much better efficiency than formed and much better accuracy than SLV. And the proposed method show similar efficiency and accuracy with the SLV and the formed. So this slide show the iteration history of object function and complex function, and the table present the secured microscale fiber-laying angle. They are strictly follow the manufacturing constant I show in this picture. And the second example is the special 120 beam composite frame structure. The structure is categorized into 7 groups in different color as shown in the picture. And the total number of design variable is 280, and the corresponding manufacturing constant number and the reliability constant number is 1, and the following the random parameter are 6, 3 random material property and 1 loading magnitude, loading the direction. This picture shows the optimized configuration. The left is the deterministic and the right is reliability. As you can see, right, for DMDO deterministic optimization, group 1, the black color is much the radius is much larger than as reliability, and for reliability, the optimization result, group 2 and group 5 in ring the direction is thicker and than deterministic optimization, and group 4 and 6 in radial the direction is also thicker than deterministic optimization. So this table show the detailed optimization results in 2 scales. This table show the corresponding comparison between the DMDO and the RBMDO. The structural cost of SLSV MNCC is about 19% higher than deterministic optimization, and is the oppositely that RBMDO is much more time consuming. So for the loading direction, seat 1 is much larger than seat 2. So this is reasonable because the structure is rotational symmetry. So seat 2 will not affect the failure, structure failure. So the last part is summary and the perspective. So in this research, we propose an efficient reliability analysis method to carry out the reliability-based multi-scale design optimization of composite frame, and we compare the proposed method with form and disagree approach. So in future research, this framework can be extended to investigate a strong singular problem and the reliability-based multi-skilled and the multi-material and multi-scale design optimization. Okay, thank you for your attention.
Thank you, Junyi. So Junyi, you can stop sharing, so we can have maybe 10 to 15 minutes for the general discussion. Is that okay, Junwu? Or 10 minutes extensions. So you can ask the last speaker, all the speakers. Already we can see some discussion in the chat room. Maybe some question already answered by the authors, by the speakers. If you have any question, you can just directly maybe unmute yourself and ask. So all the speakers, so if you are here, you can just turn on your videos, and so if you have questions, the audience, you can directly ask or show your.
I do have a question.
Yeah, please go ahead.
We are running a bit out of time. Emil, this is for you. So how stable is it? So this reminds me very much of very unstable PDE problems. And so what is, I just skimmed through the paper where you of course get it to work, but how shitty a problem is it to work with this parallel front propagation?
Yeah, so the problem itself is very stable. So the front propagation is already, it's a very mature and well-established field. But making it in 3D is just a nightmare because doing it yourself, well, it depends a bit. I chose the road of dealing with the MPI directly, and that's just that's so time consuming to you get tons of race conditions and stuff like that. So I wouldn't recommend that, but if you do it more like in a shared memory type of machine, so OpenMP, then I think it's not too bad. But yeah, it take a couple of months. Yeah.
Okay, so it's not something you will do in an afternoon.
No, for sure not.
So would it not be possible? So again, what is the main issue with not simply replacing it completely with a PDE and just propagating that guy? I mean, because it seems to me you are doing local searches, right? You have to stop and check if you are at a given point, which means that, I mean, it's not, I don't know what kind of PDE problem you could pose it as, because you have this local requirement of information. So what's your thought on that?
Yeah, so it's interesting. So it's a nonlinear PDE, and if you decouple it in time, you make it very cheap. It's like n log n to solve it, complexity, but you get this sequentiality. Actually, what I would like to try, or if I would have like another try, there is a guy that actually did 2 heat equation solves, and then he was able to basically pose a front propagation solve as 2 heat equation solves. Yeah, of course, a
linear heat equations or
linear heat equation. And so heat equation is trivial, yes, but it doesn't give exactly the right result because I'm using anisotropic front propagation, but I think there's some ways to work with that. So that would be my take if I had to continue on it.
And just out of curiosity, you said you left academia. So where are you now?
Actually, I'm at the TNO's, just Research Institute, but I'll be starting at ASML next month. So that's a semicon manufacturer. Yeah.
Cool. Well, thank you very much.
And I also want to clear up. Actually, this is weekend timed. Also in industry, it's not.
It's fun. That's what it is.
Yeah.
Thank you. Any other questions to some other speakers? Yes. Jin, do you have any questions?
I don't have
no
questions.
Okay.
I guess our colleagues in Asia are quite sleepy now. It's
okay. Yeah. So because yeah, we already is run off the time, so I think probably it's the time to stop the discussion here. And thank you all the speakers, particular Asia speaker Junji Kato. Junyi Duan's is already very late. I think it's overnight. After the mid times for Junji, it's very late. Thank you very much. And also thanks to all the participants, all the speakers. So we hope we can see each other in next webinar after the WCSMO in about more than 1 month. We hope so. Jun?
Yeah, so
any other announcements from you?
Yeah, so we will have a pause. We will return in August. So it's late August. And so I wish everyone a nice summer. It's quite in advance, but also next month we will have WCSMO. So hope to see many of you there.
Yeah.
Have a nice evening or have a nice day.
Yeah.
Bye-bye.
Thank you. Good to see you.
Okay, see you.
Thank you. See you.
See you.